Okay, guys, let us start. And it's my great pleasure to present our today's speaker, Professor Lubos Pick from Charles University Prague, and talk title on fractional Orlicz-Sobolev spaces. Please, Professor Lubos Pick, go ahead. Thank you very much. Thank you.
Thank you very much, Alexey, for this nice introduction. Please keep me informed whether you can still see my screen. I'm not very good with.
Yes, we can see it.
So I'm not very good with Microsoft Teams, but I'll do my best. Thank you again. I'm really honored and pleased by this invitation to this legendary seminar. Alexey and I, we've been meeting for a long time, and we've been talking about visiting each other. And Alexey was here, I remember, at one stage. He was a referee in some very important soccer match here in one of our conferences. So we went through a lot of things, and I never visited Rostov, but one day I'd like to do it. But it's nice to be there, at least in this distant way. So thank you again.
You're most welcome.
The talk is about on fractional Orlicz-Sobolev spaces, and let me begin with credentials. So this is a joint work with several friends of mine, Angela Alberico from Napoli, Andrea Shanky from Firenze, and Lenka Slavíková from Prague. Lenka is my former student. Now she's a colleague in the same department. As you can see, we have this perfectly balanced team according to nationality and also to gender. And together we did some research recently, which resulted in several papers and manuscripts. So the talk is based basically on some of them. So let me mention them. The first one is accepted to journal Matpures and Applied. I'm not very good with French, but it should appear this year. The next two papers on limiting behavior of these spaces already appeared, and the third one on compactness and on embeddings on domains has not been submitted yet. It's in preparation. Okay, I'll start with something which is considered classical integer order Orlicz-Sobolev spaces, and these are actually a generalization of the classical Sobolev spaces. So let's start with those. So this is a classical Sobolev space built up on a Lebesgue space. It's a collection of all weakly differentiable functions, which together with their first gradient belong to LP. And we also will need its homogeneous counterpart, which doesn't see the function itself, but it works only with the gradient. Omega here can be, say, open set in Rn. If we want to specify it, we will specify it, but mostly in this talk, it is going to be just Rn itself. So the generalization to Orlicz-Sobolev spaces works by replacing the power function t to the p, which is the base of the Lebesgue space, by a more general convex function, which we call a Young function. So it's convex function from 0 infinity to 0 infinity, with infinity as a possibility here, which is fixed by 0 at 0. Therefore, it has to be increasing and convex. And it is a generalization of Lebesgue spaces. On these spaces, there is something which is called Luxembourg Norm, which is in fact just the Minkowski thing of the unit ball. It's defined as an infimum over all lambdas, those lambdas that make this integral less than or equal to 1. So this is the Luxembourg norm of the function u in Orlicz space, and with the help of this, we can build the Orlicz-Sobolev space this way. W1A of omega is collection of all weakly differentiable functions such that U is in the Orlicz space and the gradient is also in the Orlicz space. And of course, we have also the homogeneous version, which works accordingly. Again, it sees only the gradient. These spaces, Orlicz-Sobolev spaces, have plenty of motivation for their study. They are important for the analysis of solutions to partial differential equations governed by nonlinearities of non-polynomial type. They were born by the problems that concerned nonlinearities, which with the functions growing either too rapidly or too slowly. But of course, it's in fact a more general setup. And but what is interesting, even in the theoretical, from the theoretical point of view, that they can help to shed some light on Sobolev spaces itself, especially in situations when the classical Sobolev spaces are not sufficiently rich. So let me illustrate this with an example. The good example of this is if you consider the operation of associating something that we call an optimal target space to a given space in Sobolev embedding. So that means you give me a space and I build a Sobolev space upon it, and I'm looking for the smallest possible space into which this space is embedded into. So if you look at the classical situation with regular and bounded omega, then this is the classical Sobolev embedding. W1P is embedded either into to this Lebesgue space in the non-limiting case when P is strictly less than n, and if P is bigger than n, then it is embedded into L infinity. And of course, if you allow some spaces which work with either continuity or smoothness, then you can get something better here. But in the limiting case, when P equals n, the only thing you can say within the context of Lebesgue spaces is that this space is embedded into any LQ for Q finite, but not to L infinity. So we can conclude that an optimal Lebesgue target space does not exist in this case. Well, the good motivation for studying Orlicz spaces is the note that this cannot happen for Orlicz spaces, because in Orlicz spaces there always exists a uniquely defined partner-Young function such that the Sobolev space built upon Orlicz space is embedded into this uniquely defined smallest Orlicz space. This comes from the legendary construction of Andrea Shanky. So this is Andrea's construction. You given an A, you just construct the AN. There is an almost, well, here is a formula for it. Okay, it can look like a complicated formula, but it is not really. It's a very nice formula. And in fact, if you are interested in the properties of these spaces, then anything you want to know is just the limiting behavior of this variable t, either near 0 or near infinity. And that is in for practical tasks easily computable in any possible situation. So the message is that in Orlicz spaces, there always is one uniquely defined smallest possible Orlicz space into which the Sobolev Orlicz space, Orlicz-Sobolev space is embedded. Also, there are versions of this available for spaces of functions vanishing on the boundary, and also for the space of functions defined on the entire Rn. Okay, so let's see example. So here, if we look at if we allow for target spaces, Orlicz spaces instead of Lebesgue, then this particular case, the limiting case when p equals to n, is much better than than the result that we had in the context of Lebesgue spaces, because now we have this very nice Orlicz space, and we recover this way the well-known limiting Sobolev embedding, which is due to Yudovich, Pokhozaev, Trudinger, and Strickard's. So here this sort of fills in this inaccuracy of Lebesgue spaces with the help of Orlicz spaces. Now let's go to the fractional order spaces. So there are in literature several ways how to define them. There are Besov spaces, which are defined through differences, Lizorkin-Triebel spaces defined through Fourier transform, Bessel potential spaces, which use representation formulas and potential operators, and Gagliardo-Slobodetsky spaces, which use fractional difference quotients. If you want to see some relations between these spaces, you can look at the book, the paper by Winfried Zickel and Hans Triebel from 1995, and of course there is a huge literature on this. We will focus in this talk to the last of these, that means to Gagliardo-Slobodetsky spaces, spaces defined by means of fractional difference quotients. Our motivation is comes from some recent work, because there has been some renewed interest in these papers, where authors study things like non-local minimal surfaces problems, all kinds of non-local parabolic and elliptic equations, isoperimetric things with S perimeters, and so on, so on. There's plenty of literature in those papers that I mentioned. We collected more than 80 different quotations. So references are available, and people like Bourgain, Brezis, Caffarelli, Mazia, and others are interested in these. So there's a lot of interest in studying these spaces, because the solutions of these problems that I mentioned are naturally members of these spaces. So what are these spaces? Okay, so they are based on a seminorm. So the classical Gagliardo-Slobodetsky seminorm was introduced in 1958 by Gagliardo and by Slobodetsky, and it also appears in a way in a 1955 paper by Aronshine, and it's defined this way. But if you want to find the proper generalization to Orlicz setting, then it's better to rewrite it this way. You know, the trick is to take this denominator and rewrite it this way, because now you see that this power can be easily replaced by this Young function here, and we're back in business. So the homogeneous fractional space is then defined with the help of this seminorm. Of course, it's only a seminorm, because if you take a constant function, then this gives you 0. So so collection of all functions for which this seminorm is finite is the homogeneous fractional space. Now this S here is between 0 and 1, and of course you can put this S equal to integer, but then you will hit the legendary drawback of this theory, which is important to know. Important to note, if you set S equal to integer, for example, to 1, you don't recover the integer order Sobolev space. Of course, you can define the integer order Sobolev space, where you just take the LP norm of the gradient, but you don't get it if you put S equal to 1 here. In fact, if you do that, then you always obtain infinity. I mean, no function in this world will give you a finite function if you put S equal to 1, unless this function is a constant. So one has to be very careful, and I will come to this problem later as well. There are several ways how to repair this drawback. One of them is to consider the following quantity. You take the Gagliardo oh, sorry, there should be an S. Sorry, this is my mistake here. Should be an S here, and you take this northeastern convergence of S, but you hit it by this factor 1 minus S. If you do that, then you do obtain the limit that you want at this natural endpoint. And the limit is a constant multiple of the P norm of gradient. Here should be a P. And this C depends on the dimension and P. There are papers which deal with this. It all started some 20 years ago with papers by Burgen, Brezis, and Mironescu, but there is more. Like I said, there's a lot to read about this. So this is one way how to repair. There is another one which I don't want to go into. Let me just mention it. It's a very recent way how to repair this drawback is to replace the LP norm by the corresponding Marcinkiewicz norm. This seems to be a very interesting way, but it's just available in recent preprints by Brezis, Van Schaftingen, and Jung. Okay, so back to classical setting. So this is the classical fractional Sobolev embedding, right? So if you take P non-limiting, strictly less than n over S, then you have this inequality for every measurable U. Now, of course, you cannot have it really for every measurable U, because if U was a constant, then this thing would be a 0, whereas this thing on the left would not be a 0. So, so one has to take some normalization. We use this normalization through decaying to 0 near infinity. I'm going to put a definition soon. Okay, so this looks like the most crazy formula you've ever seen in mathematics, but if you read it properly, then you're with me. This means, this red thing here means that if you take S equal to 1 in Galliardo-Slobodietsky seminorm, you do not get the this space, as I already mentioned. But even so, even though this thing is not true, then still the well-known Sobolev conjugate exponent, I mean this this exponent in the optimal space into which the Sobolev space is embedded, is recovered. Yes, it's the same. You can so there is some correspondence here, even though there is no correspondence here, right? So this is good to notice, because we will soon observe a similar behavior in the Orlicz setting, right? Okay, so what about the fractional Orlicz-Sobolev embedding? So far we've seen the classical Sobolev embedding, the fractional Sobolev embedding, and now it's time for fractional Orlicz-Sobolev embedding. So, okay, so you give me the S, you give me a Young function, then the fractional Orlicz-Sobolev seminorm, which just generalizes the Galliardo-Slobodietsky seminorm, is defined this way. So we use the idea of the Luxembourg norm. We take infimum over all lambdas such that this thing here is less than or equal to 1. And of course, here you can see the way I rewrote before this Galliardo-Slobodietsky seminorm with the help of the P around here. So this P is replaced by an A, and the rest is just natural. So this is the Orlicz-Sobolev, fractional Orlicz-Sobolev seminorm with this non-integer S. And then we define the homogeneous space. Now, what about this decaying to 0? So now it's time to define it. We will need a space, a subspace of this that contains only functions that decay to 0. The reason I have already explained is because if you allow constants here, you have a problem with the embedding and with the inequality. The inequality cannot be true. So that's why we do this. That's why we restrict ourselves to these functions. How do we define them? Okay, we define them the following way. We want that the measure of the level set is always finite for any t. So a function has to somehow go to 0. It cannot be constant on a set of infinite measure, right? Any level set is a finite measure. So this is what we want. This is how we deal with this is how we forbid the constants, right? Okay, so our first result says that the situation is similar like in the integer order case, that if you give me this non-integer fractional Orlicz-Sobolev space, then we can always find an uniquely defined optimal Orlicz target space for it. Okay, so we will need some restrictions on the Young function, this one and another one here. Let me explain what these restrictions are. Okay, so this restriction amounts to requiring that A is a non-supercritical growth, which means that if you put for an A a power, then it corresponds to this inequality. Now, important thing to notice here is that the limiting value P equal to n over S is allowed here. Okay, it is not allowed by this thing here, but that works only near 0. So that is not so important. Of course, on Rn it is important, but still, if you're interested in local singularities, then you can cook this from water, and this is something which is important. So it's good to know that the limiting value here is allowed. Okay, so then we follow Andreas' construction with 1 replaced by an S here. What we obtain is the optimal fractional Sobolev conjugate of A. Now, of course, here is this parameter S. And again, like this is the same phenomenon that we saw in Sobolev spaces built on Lebesgue spaces. Even though these two guys are not the same, with an A here, right? Even though they are not the same, again, if you put S equal to 1, then we recover the conjugate Young function which Andrea obtained in his classical construction. So it's time for the first main result. So I can now present the optimal fractional Orlicz embedding. So you give me an S between 0 and 1 strictly, and a Young function which satisfies those restrictions. Then we have the embedding of fractional Orlicz-Sobolev space into Orlicz space with this function n over S, which we construct in a way that I already described. And of course, this embedding is quantified by the inequality. Moreover, this target space is the optimal, which means smallest, of course, target space for this embedding or for this inequality among all Orlicz spaces. So there always is one. And let me just mention that this second condition here is actually necessary for an embedding into any Young function. But in fact, it is necessary for this space to have any rearrangement invariant target partner here. So if this is not satisfied, then you cannot put here any reasonable target partner, right? No, at least not within rearrangement invariant spaces that are also called in Russian literature often symmetric spaces. Let's go for some examples. So, okay, so if we go back to the power type function, then we recover what we already know. But because the limiting value is allowed, we also have this. We also get this limiting result. So this is what had been known, but this is new. And again, we add this information which had not been known before, that this is optimal. This is the smallest possible Orlicz space. You cannot put any smaller space. If you put smaller Orlicz space here, then the embedding is not going to be true. Okay, with some more complicated Young function, power logarithmic, then again, of course, some restrictions are necessary because you want your Young function to be convex. So that's why in the case p equals 1, alpha has to be non-negative. If p is between 1 and n over s, then alpha can be anything. But if p is equal to n over s, then we want alpha less than or equal to n over s minus 1, because otherwise the space is too good and we go to infinity. So with these spaces, we obtain non-trivial interesting results. Again, we can add the information that all the targets are optimal within Orlicz spaces. So if the pooling, the pool of competing spaces is that of Orlicz spaces, then these are the best ones that you can obtain there. This recovers some other results. For example, the legendary paper, 25 years old, by Fusco, Lyons, and Bordone, and also some work of David Edmonds, Peter Gurka, and Mirek Opitz on fractional spaces, Bessel potential spaces, similar spaces that appeared also in mid-90s in the Indiana University Math Journal. Okay, let us mention that if we allow ourselves some still more general or still different classes of function spaces, then improvement is still possible, even in classical setting. But in classical setting, this is well known. But in the fractional setting, fractional Sobolev, not Orlicz, just fractional Sobolev, this is rather recent result by Rupert Frank and Robert Seiringer, who were able to prove that actually you can replace the Lebesgue space here by a Lorentz space, which is smaller. So Lorentz space is equipped with this norm. U star is just a non-increasing rearrangement of a function. And since this space is well known to be strictly smaller than the Lebesgue space, then we can conclude that this is really a non-trivial improvement. Now, this was known by work of various authors in 1960s, like Hunt, Petre, O'Neill, and others in the classical setting. But like I say, in the fractional setting, it's rather new, 2008. And so, of course, there is a question, what happens in the Orlicz setting, fractional Orlicz? So we can actually extend this question to seek the optimal rearrangement invariant target space. So this Y here is now represents a general rearrangement invariant space, and we are looking whether we can get a optimality there. Let us recall that what does it mean, this rearrangement invariance? Rearrangement invariance means that the norms of functions is the same when their level sets are the same, or non-increasing rearrangement is the same, whatever. So, for example, Lebesgue spaces, Orlicz spaces, Zygmunt spaces, Lorentz-Zygmunt spaces, Lorentz spaces have this property, whereas spaces like Sobolev spaces, Biesov spaces, spaces of continuous functions, Helder spaces, BMO, they don't have this property. So basically, spaces that have this property measure just the size of the function, not its continuity, smoothness, or oscillation. So it turns out that we are actually able to do this, but we have to work slightly different with slightly different Young functions than before. We define another. As you see, we are using a lot of symbols here. Another Young function this way. Again, this looks complicated, but again, it is not so complicated if you want to evaluate this in a limiting sense, in limiting behavior near infinity or near zero. It's not a problem. You need a L'Hopital rule and a little bit of calculation, and in fact, this function is always less than or equal constant times A. And if if A is far from the critical line, then they are the same. The critical line here is quantified by Matuszewska-Orlicz index. So if this index is strictly less than the critical one, then the functions are the same. I can give some examples. If A is just a power, then the A hat is also a power. I mean the non-limiting power. If A is a limiting power, then you start losing. Then you are losing some logarithms here. So with help of these, we can formulate our second result. So we formulate this norm here, or this functional, whatever. It's we call this an Orlicz-Lorenz space. So you can observe that this is done in the same way as Lorenz space was born from Lebesgue space. So this Orlicz-Lorenz is in the same way born from Orlicz space, but we replace A by this A hat here. And then, having done all that, we can formulate the result. So again, this fractional Orlicz-Sobolev space is embedded into this Orlicz-Lorenz space, and of course we have the corresponding inequality again for every function with a proper decaying at 0. And this time the target is it is no longer an Orlicz space, it's an Orlicz-Lorenz space, but this time it is the optimal Ri target space. So it is optimal in a more general setting. Yes, the pool of competing spaces is now wider. So this is a stronger result than the previous one. Let's compare the theorems. So like I say, this result is stronger. That means that the first theorem follows from the second one, but it's not trivial. One has to prove that this Orlicz-Lorenz space is embedded into the Orlicz space, which is not trivial, but it is not terribly difficult either. So we prove this. So in this sense, the first theorem follows from the second one. This latter means the second theorem. The second theorem, the stronger one, is a consequence of a Hardy type inequality. The Hardy type inequality is the core of the proof of the embedding results. So let's formulate it. And let's look, let's compare it to the classical situation. So in the classical Hardy inequality, the one that I have in mind, of course there are plenty of Hardy inequalities, is this one. Then there is the fractional, sorry, then there is the fractional version of it, which is, you know, you see the S here instead of 1 here. Now this has been known. This is a 20-year-old result by Mazia and Shaposhnikova, this fractional version. And now, how does it look in fractional Orlicz-Hardy? Well, okay, let's have a look. This is our next theorem. If you put an Orlicz function here, a Young function here, so you have an Orlicz-Sobolev seminorm, then the corresponding thing for the Hardy inequality turns out to be this Orlicz norm with this A hat Young function. Then the corresponding inequality is this one. Maybe you want to notice this constant here, 1 minus S. So we can prove this, and this is the core of the proof of the embedding results. Right. Let's have a look at some examples again. If we take this power logarithmic thing, now this corresponds to what I said before. If we are in a non-limiting situation, quantified by the fact that Matuszewska-Orlicz indices are smaller than the critical ones, then the function is actually the same. This is, I have already said this in a more general formulation before. But once you get closer to the critical line, then you start losing. Yes. So instead of alpha, there is alpha minus something here, and if you go to the so-called second order limiting situation, then you lose even more. log function comes into the picture, and so on, so on. So these are interesting and nicely obtained results. And of course, this is all behind that embedding theorem. We can shortly outline the proof. What is it based upon? Well, okay, so we start with this. So this is the Orlicz-Sobolev norm, and the embedding is just this inequality. Where do we get it? Well, we apply the Hardy inequality to a radially decreasing rearrangement of U. We use the Steiner symmetrization here, and we use the Poya-Segő principle, right? As the principle of two Hungarians, 1950s. Poya-Segő principle tells you that by symmetrization you're not losing in this fractional Sobolev Orlicz seminorm, which of course we have to prove. So we prove this, and then on the other side you have just equality. So this inequality is obtained from this inequality by taking an identity on the left and inequality, Poya-Segő inequality, on the right. So this is just part of the result. This is just embedding. The second part of the result, the optimality, is proved through a general necessary condition, which is often called a reduction principle. Here it is enough for us to use just one implication, even though the second one works as well, but we are not using it. Reduction principle means that you take the difficult inequality of functions of several variables and you turn it equivalently to a Hardy type inequality, or say a boundedness of an integral operator working with functions of a single variable on an interval. Yes, so this has been used a lot in last 2 decades or so, and it works here as well. So that is the core of the proof of the optimality part of the theorem, and this is, let me say, highly non-trivial, because we have to, given a U, we have to, given an F, we have to formulate or construct a appropriate U, and then calculate a lot of fractional derivatives, which is technical, and there are some technical lemmas behind this. Okay, let me just add that we have other results which I'm not going to talk about in detail. One can go to higher order spaces. We also obtain corresponding results for on bounded sets, and also we have results that characterize compact embeddings. I don't have time to talk about these, but let me just say that for higher order embeddings, we use an iteration principle, which is interesting. We combine their results for that we published before with Andra and Lenka, with a special reduction principle by another student of mine, Zdeněk Mihula, which appeared recently in his paper published in Proceedings of Royal Society of Edinburgh. So this is all I want to say about these, and now let's go to another problem. Still have some time. I'd like to say a few words about the limits. I already said several times that with these seminorms, one does not recover the endpoints if you take s equal to 1, but in fact, I did not mention the other endpoint, s equal to 0, but in fact, even there, one does not recover the endpoint. So these things are interesting, and they have been studied in the classical sense. So how do they work in the Orlicz setting? Let me just mention a few words about that. Okay, so So like we already mentioned that they do not reproduce these spaces, but however, okay, so let's consider now the limit at 0. Yes. Okay, the limit at 1 was done first by Brezis, Burgen, and Mironescu, and the limit at 0 was done shortly afterwards by Mazia and Shaposhnikova in the classical setting. And this result tells us that if you hit the seminorm, the Galliardo-Slobodetsky seminorm with an S by an S, and then you take the whole thing to 0, then you actually do obtain a constant multiple of the Lebesgue norm of the function raised to p. This constant is interesting, and it's nice to notice this p in the denominator, because it the constant is very precise, and the Orlicz result has to verify this. So this p has to be recovered. Omega n is the volume of the unit ball in the n-dimensional unit ball. Okay, so question is obvious. What about the limits in the Orlicz setup? Well, we need another Young function, and this one comes this way, and this maybe, if you look at this formula, if you do this to a power, then what you obtain is exactly, you get this constant here, 1 over p, right? So this is how we recover the classical result. These two functions are always equivalent. There is this very simple sandwich for them, and we need a delta 2 condition here. So let me just recall what is the delta 2. The Young function is called satisfied delta 2 if it satisfies this. If you take a double trig here, then it has to be bounded by a constant times the single trig. Of course, powers have this property, but functions that grow rapidly, more rapidly than powers, do not necessarily have it. Typically, exponential functions, either near infinity or near 0, are not delta 2 functions. A lot of this is done in the classical monograph by Krasnoselsky and Rutitsky on convex functions and Orlicz spaces. So here's the theorem which recovers Mazia-Shaposhnikova result and which deals with the limit near 0. If you give me a function in in one of these spaces, in the union of all these spaces, and I take a limit s takes to 0, and I hit this by s, then we recover that. Here this 1 over p is hidden in this a bar, the way I mentioned before, and in fact it's written here. So this does recover Mazia-Shaposhnikova result when you take a power for any p bigger than or equal to 1, since then you get exactly this function. So this constant comes out precisely, right? The precise constant is recovered here. What about this delta 2 thing? Is it necessary or not? Well, it's maybe good to mention that there are some other recent works, usually by Ariel Salort and his co-authors, where some estimates are established, but additional assumptions are required. These additional assumptions are the sublinear growth near 0 and delta 2, but they are in fact not necessary. Whereas our result provides a full answer, because we can show that the result can fail if you drop delta 2 condition. Here is a theorem. It's more an example than a theorem, but it says that we can construct a Young function which is not in delta 2, and then the thing fails. We still have this inequality, but the limit is equal to infinity. We don't prove this for any Young function outside delta 2, but we prove it. We prove that there exists one. let's go to the other endpoint. This has been mentioned several times already. Endpoint near 1 from northeast. It's this thing quoted to Brezis, Bourgain and Mironescu. So it was initiated by their paper where they proved this. I've already, sorry, I already mentioned this. So this is just more precise formulation of it, right? So you take the Galliardo Slobodetsky semi-norm, hit it by 1 minus s, look at the northeastern limit, you go northeast to 1, and then one does obtain, as I already mentioned before, a constant multiple of the LP norm of the gradient.
Right.
Now whole thing is raised to p, sorry, I didn't say that. Now, the precise version of this k is written here. Sorry. K is given by this formula, where S is just the n-dimensional unit sphere, H is the n-1 dimensional Hausdorff measure, and E is anything. E is any point on the sphere. The result does not depend, the constant does not depend on the exact value of this E here. Brezis, Bourgain and Mironescu show that there is actually a converse result, but one has to be careful here. P has to be not equal to 1. P has to be bigger than 1. If P is strictly bigger than 1, then, then there is this interesting converse result in their paper, that if the limit inferior of this thing is finite, then the function has to belong to the Sobolev space, right? W1P. So their limiting result works both ways. If P is equal to 1, then this is no longer true. I mean, you cannot put W11 here. It's not true. But you can replace W11 with its usual traditional replacement, which is the set of BV functions. If you do that, then the result works again. How does it look in the Orlicz setup? Well, question is obvious. What happens if you go northeast? Well, again, another symbol, another Young function. We calculate another Young function. Then, okay, some observations. The right-hand side of this is not dependent on this E. E can be anything on the sphere. It's always equivalent to A. Inner equivalent on the left, outer equivalent on the right. And here's the theorem. Sorry, there's some overflow. I didn't know to make it smaller. So, this limit, the northeast limit at 1 works in Orlicz setup with no restriction on A. Yeah? No restriction on A. No sublinear growth near 0 is needed. No delta 2 is needed here. However, okay, some comments here. If this property holds with sufficiently large lambda, here is a lambda here. There has to be lambda there, and there is a bound for it. So we only obtain this for big enough lambdas. However, if A isn't in delta 2, then this thing only ensures that this is true for sufficiently large lambda. So this is completely natural. And of course, if A is in delta 2, then you obtain it for any lambda in a traditional way. So this improves the result that I mentioned of Fernandez, Bonder, and Salord, which only allow this for delta 2 functions and extra unnecessary hypothesis, which is the sublinear growth near 0. What about the converse? Well, like we said, the converse does not work for T to 1. I mean, for t, for the linear thing. So there has to be something which reflects this in Orlicz spaces. What is it? Well, it's the definition which appears in the, for example, in Krasnoselsky-Rutitsky, and which is usually called in literature an N function. You require a sublinear growth near 0 and superlinear near infinity. So if you take a power, that means that simply that p is bigger than 1. And if you require that, then the converse result works. Here it is. A has to be an N function. A cannot be a general Young function here. It has to be an N function. Well, of course, there has to be something, because otherwise we would get a result which we know is not true. So there has to be something that prevents this LA from being L1, right? So the converse works in this case. And let me just say that if A has a linear growth, either near infinity or near 0, then again there is a counterpart, which is something we call a relaxed functional, which works with the BV functions, but I would omit the details for this. So that would be all from me. I'd like finally to mention that we have, like I say, this is some recent research of this team of 4 people. We used to meet a lot. Now, of course, in this situation, it's difficult to meet, but we still enjoy working together. Some of us have already given lectures about this. In particular, I'd like to express my gratitude to Andrea, who gave a wonderful lecture, and I used a lot from his lecture to prepare slides for this one. I actually stole some of his slides, but in this setup, I would like to quote a friend of mine, Jiří Bouchala from Ostrava, who says that the theft is the highest expression of respect. So that will be all. My final message is this: keep the world beautiful. I took this picture a week ago. This is something that grows not far from Prague. And in order to get there, I need to break the rules, because we are not supposed to travel, but I just couldn't help it. I mean, it's too beautiful. Thank you very much.
Well, thank you. Thank you very much for a very nice talk. Thank you, Lubos.
Спасибо огромное.
Okay, thank you. Please, questions. We have time for questions.
I have a question. Is it okay?
Yes, please go ahead.
Yeah. In our book, you know, in chapter 5, it's about fractional order Hardy inequality. And your lecture is extremely interesting. Of course, it's some new questions for me here, this with optimal targets and such things. So from my point of view, all of this works in the following way. You know, classical Hardy inequality, as you wrote it, or in differential form. The first results by Grivard and Yakovlev, it's this, you know, it's something that the left-hand side in Hardy is less than such as fractional norm. But maybe it's a new idea to investigate, you know, in the book we have also, this is we call left-hand side fractional or Hardy. But when S goes to 1, then you go to the right-hand side of Hardy. So you have a right-hand side Hardy also, and we have a very simple proof of this in the book. Right-hand fractional Hardy. And maybe you have the same question there, you know, it corresponds when S goes to 1 in your. So this results when S goes to 1 should be compared with this, you know, and maybe you get some interesting embeddings. But this is in the classical situation. It's not this. If you extend this also to this Orlicz setting, maybe you get some interesting.
Well, thank you. That sounds interesting. We definitely have a look at it. It's remind me again which book it is. The one with
book with from 2017 with Alois and Natasha.
Yes. Okay.
I have in chapter 5. In chapter 5, you have it for sure. Yes.
Have a look at it.
In chapter 5. It's a simple proof we have of this, what we call the right-hand order Hardy. And it should be some similar questions there.
Sorry, I was looking at my bookshelf. I do have it there, yes. I'm going to, it's the black cover book, yes?
Yeah, yes. So it looks like.
Is it this one?
This one.
This one?
Yes.
Okay, I'm going to open it right now. Thank you.
Chapter 5.
Chapter 5, sure.
It's exactly connected to this, but it's not done anything in this direction, you know, with this situation you have. But you have a right-hand side also of this.
Okay. Gonna have a compare this, sure. Nothing to do anyway for this evening.
Thank you, Lars-Erik, for a question. Please, more questions, guys.
Lubos, is something known when we replace fractional order derivatives or fractional order by some more general function of differentiation?
Well,
instead of parameter s, instead of power function, some more general. Is it known something?
I'm thinking. I don't know if if this exact setup, but I would have thought that some kind of you know, like interpolation results and things like that, interpolation spaces, there might be some sort of general, but I'm not aware of any results of that kind that would involve optimality of targets. That I don't know. But of course, what I mentioned in the beginning, that there are several ways how to define fractional spaces, and there's you know, plenty of results for those. So I'm sure something in this direction will be there. Probably one would have to go through books by Hans Triebel and similar literature. I'm not aware of anything offhand, but I would be very surprised if anything was done for optimality in this direction, because that would be difficult, I think, in that generality. I don't know, maybe someone in the audience knows more. I don't know.
Okay. Lubos, may I have a small question? You mentioned about reduction from the Rn to a bounded open domain. And my impression was that you just have to delete some condition, like you have some integral conditions, one from 0 to something, and another condition from something to infinity. And my impression was that you just cancel this condition with infinity and you reduce the result to a bounded domain. But maybe I'm wrong, because you said that a bounded domain needs more accurate study. So it's not like just cutting out some conditions caused by infinity and you have the bounded results, no?
Well, this thing is a bit more complicated than it looks, and it's not quite finished. But of course, if in sense of this of these bounded domains, you're interested only in singularities, local singularities.
Yes.
Therefore, you are allowed to play with your function near zero. So whatever condition, you can cook it. I mentioned this in the talk, that if you're not interested, I mean, if you work only with local singularities, then you can change the Young function near zero. But we discovered some strange phenomena concerning this. Even when when a function should not affect the results, there are some technical obstacles that we we believe the space is affected by it, but we believe that the embedding should not be. We have something to this account on Arxiv, but we did not publish this yet.
Okay,
this part of the result. But you can find it on the Arxiv.
Okay, thank you. Thank you. More questions, please, guys. You can raise your hand, or you can just go ahead and place your question. Okay, if you don't have more questions, then please turn on your cameras. We can take pictures of all of us. And let us thank again to Professor Lubos Pick for a very nice talk. It's our great pleasure to have Lubos. We have been speaking a lot of time with Lubos to invite him at our conference, or as he said, I was intending to visit Prague, but as you see with these COVID conditions, we cannot travel, but we can see each other through internet. It's great that Lubos agreed to have a talk at our seminar. It's our great pleasure. Thank you, Lubos, again.
My pleasure. Thank you. Great honor for me.
Thank you.